So in the last 10 minutes of class, I'll pass back the exam and we'll go through a couple of the problems. And I'll talk through like how it went and what the final is going to look like as well. But until then, so the first 40 minutes, I'm just gonna keep on going through chapter 9. So we started talking about differential equations in class on Monday. And so the homework that's due next Monday, this is going to be going over section 9.1. And I think there's like one or two problems that cover the very beginning of section 9.2. So that's all we need to cover today. The main point of section 9.1, I guess before I continue, does anyone need the notes from Monday? Yes, we started talking about differential equations. And so we're kind of like, I mean, we're going to still be looking at integrals, but the point of these problems isn't going to be giving you like interesting integrals to solve. Usually the integrals are easy to compute for these sections. So like while integrals will show up, like we're really going to be looking at derivatives and ways of solving differential equations, at least for chapter 9. And then chapter 10, we're looking at infinite series. So there's going to be like towards like the last two chapters of the book, they kind of throw a lot of new things at you. So it's important that you kind of stay diligent in keeping up with the material. Like if you wait to kind of like cram for the final, it's going to be pretty disastrous, I think, just because there's so much new content that doesn't rely on like integrals or derivatives. So it's like learning things from step one pretty much. And so the main kind of differential equations we'll be looking at really throughout this course are going to be separable differential equations. And see, so these are just differential equations of the following form. So if you have dy dx is equal to a product of two functions, f of x times g of y, the thing worth noting is that this is a function with respect to x, and this is a function with respect to y. So what we saw on Monday is if you want to solve a differential equation of this form, what you do is you put everything involving a y on one side of the equation and everything involving an x on the other side of the equation. So if we have like dy dx is equal to f of x times g of y, if we wanted to move everything with a y on the left-hand side, we'll divide both sides by g of y, and then we'll multiply everything by dx to the right-hand side. And so if you do this, you get 1 over g y times dy is equal to f of x dx. And then to get rid of the dy and the dx, you just integrate both sides like this. So we went through a couple of examples, and we'll go through a couple more examples today. All right, so we went through this first example, second example, right? Like I think the second example is more important to look at, right? We have a function of y multiplied by a function with respect to t. If we wanted to solve this differential equation, we'll divide both sides by y, and then multiply both sides by dt to get the following equation. And then you just integrate both sides of the equation, and then you solve for y, right? So like the main point of these problems is you want to solve for y. Whatever function you're taking the derivative of, like this is what you want to solve for. Okay, so we went through an application, and let's just keep on going. So I'm going to skip this next example. So it talks about, I don't even know, like, hold on. Torricelli's law. We're not going to care about Torricelli's law. So you can skip this next part and this next example. We're not really going to care about it. If we have time, maybe we can look at it later. But we're going to move on to talking about exponential growth and decay. And you might have talked about this a little bit in Calculus 1, but we'll be deriving the equation for when we have a rate of change that's proportional to where your function y is. And so there's going to be many phenomenon like population or like decay or something like that that are going to be modeled by the following differential equation. So we're looking specifically at differential equations of the form of dy dt is equal to k times y. And so this is really just saying that the rate of change of y is proportional to the amount of y present, right? Like we're really saying, and this is, I'm just writing the same equation out, but some people like the prime notation versus like the Leibniz notation, right? We're saying like the rate of change is equal to something times y. So that means these two things are proportional to one another. And so some examples like this includes like this models the growth of a population, the spread of a computer virus, the decay of a radioactive substance, and the elimination of a drug from a patient's bloodstream, among a number of other things. And so the growth and spread is represented by this constant, or the proportionality is represented by this constant k. Or I'm kind of like missaying this. So like the main point I'm writing about or saying like in this paragraph is like if the constant k is positive, that means we have exponential growth. And if this constant k is negative, it means that we have exponential decay or elimination, right? So the sign is going to depend or tell you whether or not you're growing or if it's decaying. So this is like growth, or maybe I should write it like this. That was kind of vague. So if we have k is greater than 0, it means we have growth. If we have k is less than 0, that means we have decay. So there's exponential growth and there's exponential decay, and it depends on your value of k, like this exponential or like this constant. Okay, and so the main thing we're concerned with is how do we solve such a differential equation, right? Like we're given dy dt is equal to k times y, and so we want to solve for y, but really we just have that this is a separable differential equation. So even though I'm calling it like exponential growth and decay, and it's like a special class of differential equations, it's really just a subclass of what we already looked at, right? Like it's just a subclass of like this kind of differential equation. And so you don't want to solve this differential equation every single time you see it. So we're going to come up with an equation that will always give you like the general solution to this. And so you just solve it as you do for the other examples that we did. So we have dy dt is equal to k times y. And so what we're going to do is we're going to write everything with the y on the left-hand side. So we'll divide both sides by y. And then we want to make it so everything with the t is on the opposite side. So we'll multiply both sides by dt. So we end up getting that dy over y is equal to k times dt. And so where we go from here is once you're at this point where the variables are separated from one another, you want to integrate both sides of the equation. If you integrate both sides of the equation, you get that the integral, instead of writing like dy over y, I'll just write 1 over y dy is equal to the integral of k times dt. And so you integrate and then you solve for y. So on the left-hand side, we have the natural log of y. And this is equal to the integral of k with respect to t. So that's going to be k times t plus c. And so if we want to solve for y, all we need to do now is just get rid of the natural log. So you just exponentiate both sides of the equation. So this is going to be e to the natural log of y is equal to e to the kt plus c, which is really saying we have y is equal to e to the kt plus c. And so usually you don't write out, I mentioned this a number of times on Monday, you don't write things out as like e to the kt plus c. Like what you do with this e to the kt plus c is the following. So you'll see this when I write out the equation on the next page, but this is like e to the kt plus c. So you want to use properties of the exponential function to make this look a little bit nicer. So this is the same thing as doing e to the kt multiplied by e to the c, right? If you multiply two exponential functions with the same base, it has the effect of just adding the exponents. And then this itself, like this term here, e to the c is just a constant, right? And so we're going to say this is equal to some constant. What do I say on the next page? We're going to say it's equal to a constant represented by the quantity d. So this is really equal to d times e to the kt. So I'm just condensing this chain of equalities. We ended up finding that y ends up being equal to d times e to the kt. And so whenever you have one of these differential equations, so a differential equation where the rate of change is proportional to whatever your quantity y is, the solution is always going to be given by the following. So you can always just you can skip all of this here and just write out like y is then equal to d times e to the kt, right? And then you just have to determine what this d is going to be and what this k is going to be based off of the information that's provided. Okay, any questions about how we derive this solution? Okay, and again, this is a infinite family of solutions that one has, because as d varies, you end up getting different solutions. So this is graphed on the next page. Okay, and so from the previous example, what we have just shown is that the general solution to dy dt is equal to k times y, ends up just being equal to y of t is equal to d times e to the kt, right? So this is what we've just shown, and you can use this, you're going to use this over and over again. This is a really common class of differential equations that we'll be looking at. And so the point is, again, like as I just said, we're really finding families of differential equations. And so depending on what your constant is going to be, it's going to give you a different solution, right? And so we're assuming like in this graph that we have exponential growth. So we have like k is always greater than 0. And then all of these lines correspond to different values of d. So when d is positive, you're going to get positive exponential functions. If d is negative, you end up getting negative functions, right? Like if d were equal to -1, it would probably look something like this. Right? You reflect across the x-axis. And so as I was saying before, like when k is greater than 0, that means that the function y is equal to d times e to the kt, models exponential growth. And if we have that k is less than 0, it means that we have exponential decay. Okay, and so let's go through a couple of examples where we utilize like this general solution to the differential equation. So for this next example, we have a number of different things that it wants us to solve. So in the laboratory, the E. coli bacteria grows such that the rate of change of the population ends up being proportional to the population present. And so the moment you see like the population is proportional, or the rate of change of the population is proportional to the population present, you should immediately be thinking like we're in this situation right here, right? And so that means we know that y of t is going to look something like this, but I'll write that out later on. And then furthermore, so that will give us what the general solution will look like, but we also want to know what the particular solution will look like. And so that's where this comes in. So we're assuming that we have 1,000 bacteria initially, and then we have that 1,500 are present after 1 hour. Okay, and so it gives us a bunch of information. And so what it wants us to do is it wants us to determine what the population function is going to be. So it wants you to determine the population after t hours. And then there's other questions like how large is the population after 5 hours? And then how long does it take for the population to double in size? Okay, and so we're given the following function in the beginning. So we have p of t. This is equal to the population after t hours. And so we're told in the beginning of this problem that the rate of change of the population is proportional to the population present. And so what this is telling you in like a mathematical way is that we have p prime of t is equal to k times p of t, right? This is what it means for the, maybe I should do like a underline or something like that, right? So the rate of change of the population is proportional to the population present. So that's how I'm getting this equation right here. It's like what I'm underlining in green here tells you why we have this equation underlined in green here. So the words are telling you that. And so once you know that we have this differential equation, like p prime of t is equal to k times pt, what this equation above tells us, like the equation at the top of the page tells us that we know that p of t is going to be equal to d times e to the kt. Like we already know, because the differential equation is of this form, we already know what the general solution is going to be. So we already know that the general solution is going to be p of t is equal to d times e to the kt. Right, so I'm just using this equation we used in the first part. And you could derive this as well. Like if you did the exact same thing we did on the previous page, you solve this differential equation for p of t, you would end up getting the exact same equation. But you can bypass all of that because we've already derived the equation. Okay, and so what we want to do is we want to determine what d is going to be, and we also want to determine what k is going to be. Right, like looking at problem 2, it's asking how large is the population after 5 hours. So you would plug in t is equal to 5, but we wouldn't know what d is equal to, and we wouldn't know what k is equal to. So it wouldn't really give us a number. So like the next goal that we have is we want to find the following 2 quantities. So we want to find d and k. Okay, and so if we want to find d, you should be thinking, maybe you've seen this before in like a previous math class, but like d is really going to correspond to whatever your initial population is going to be. And I'll show why here. So in the beginning, we're told that we have 1,000 bacteria initially present. So this is telling you that the initial population is equal to 1,000. So what this means is that we have that 1,000 is equal to P evaluated at 0, right? This is the population after 0 hours is going to be equal to the initial population. And then we also know that P evaluated at 0 is equal to D times E to the K times 0. But like e to the 0th power is just equal to 1, right? And so this is just equal to D. And so this chain of equality shows that 1,000 is equal to D, or like D is equal to 1,000. Right, so this is how you determine what D is equal to. And in general, if it just tells you the initial population is 1,000, you can just write in 1,000, like D is equal to 1,000 right off the bat. Like it always works out this way. Right, and so this is telling us now that we have that piece of T is equal to 1,000 times E to the KT. And then the next thing we can solve for is going to be K. So if we wanted to solve for K, does anyone see what we would do? Like what information do we make use of? For
into it, like T equals 1, and then yeah, you just solve it.
Yeah. So you plug in, like we're told in the beginning that, or we're told that 1,500 E. coli bacteria are present after 1 hour. So you just do the exact same thing over again. So we're told that we have 1,500 bacteria is equal to P evaluated at 1. And then we know P evaluated at 1 is just equal to 1,000 times E to the K times 1. But that's just E to the K. So I'm just going to write it as E to the K. And then from there, you can just solve for K. Now we have an equation in terms of a single variable, and we can solve for what K is going to end up being. So you divide both sides. If you want to solve this equation, you divide both sides by 1,000. So you end up getting that this is going to be 1.5 is equal to E to the K. And then you just take the natural log of both sides to get rid of the E that we have. So we end up getting that natural log of 1.5 is equal to K, which is really saying, I like writing it out as a decimal, that K is approximately equal to 0.405. Okay, so we found what D was equal to, and we found what K is equal to. And so now we have a particular solution to the differential equation. And so this means that we have that P of T is really equal to 1,000 times E to the 0.405 times T. So this is the particular solution. And that's part 1, right? And then part 2 is really just, well, before I go into part 2, does anyone have any questions about how we found this equation? Yeah, so usually for these exponential growth and decay problems, there's 2 things you have to solve for. You have to find what your K is equal to, and you have to find what the D is, what like the constant D is equal to. And then once you determine both of those things, now you have a particular solution. So maybe I should write out like this is like the particular solution. It doesn't rely on any constants anymore, whereas this was the general solution. Okay, and so now that we know what the particular solution is, the second part of the problem is it asks you to determine how large the population is after 5 hours. So all you have to do now is you just plug in T is equal to 5. When you plug in T is equal to 5, you just get a number, right? And that'll tell you the population after 5 hours. So for part 2, we have that P evaluated at 5. This is just equal to 1,000 times E to 0.405 times 5. So this number ends up being equal to 7,576. Right, so once you have the particular solution, it's pretty easy to work around with these things. Okay, so that's part 2. And then part 3, this is a little bit more involved in that we're actually going to have to solve for what T is equal to. So for this part, for part 3, it wants you to determine how long it takes for the population to double in size. And so the initial population we had was equal to 1,000. And so for it to double in size, we want to solve for t when the population is equal to 2,000. So we had like the initial population, I'll just write this out. The initial population was equal to 1,000. And so this is telling us that the goal for this last part of the problem is it wants to solve for t, or maybe I should say, like, we want to solve 2,000 is equal to p of t for t, right? So you multiply the population by 2, and then you want to solve for what t ends up being equal to, right? And so you just, I mean, from here, I mean, it's just algebra, right? You don't have to do any calculus or anything like that. So we have 2,000 is equal to 1,000 times e to the 0.405 times t. And so we just need to solve for t. And so what you can do to begin is you divide both sides by 1,000 to get that 2 is equal to e to the 0.405 times t. And then you take the natural log of both sides to get rid of the e. So you have natural log of 2 is equal to 0.405 times t. And then you just divide both sides by 0.405. So you divide both sides to get natural log of 2 over 0.405. And this is equal to what t is equal to. And so this is giving you a number, right? Natural log of 2 over 0.405 is just a number. And so if you plug in this, if you plug this number into a calculator, you find that t is equal to 1.71 hours. So this is how long it takes to double the population. And so you can note, like, we were able to solve for what this equation is going to end up, or what t is equal to right here. But you can really just note that the amount of time it takes to double is really just like the natural log of 2, where this 2 comes from the fact that we're doubling the population, right? We took like 2,000, like 2,000 is just 2 times 1,000. So if you divide by 1,000, you just get this 2. And then we're just dividing by k, right? So if you want to find the doubling time, it's always just going to be the natural log of 2 divided by whatever your k is going to be, which I have written on the next page. Any questions about this problem before we move on? Okay, so yeah, so you can always derive what the doubling time is going to be, but you can also just note that what we just found was that the doubling time is just equal to the natural log of 2 over k. Similarly, if we wanted to find the half-life, so maybe I should define what these terms actually mean, right? I'm getting ahead of myself. So like in the previous example, we computed the time it takes for the initial population to double. In exponential growth, the time to double in size is called the doubling time. So we just computed the doubling time. Similarly, in exponential decay, the half-life is the time it takes for an initial amount to decrease to half its size. And so if you want to find the half-life, it's just going to be the natural log of 1/2 divided by k. And then what we found in the previous example is the doubling time is just going to be the natural log of 2 divided by k. So again, you can always derive these equations, right? But you can also just remember what these quantities always end up being equal to. So I guess like the thing worth noting is that it doesn't depend on whatever the initial population or quantity is, right? Like the initial population doesn't show up in these equations at all. What matters is the ratio between like the double time and the initial population, which is always going to just be 2. Okay, let's go through another example before moving on to the next section. So the next example, it's pretty similar. So we have like bismuth 210 decays at a rate proportional to the amount present. A sample of bismuth 210 that initially had a mass of 1,000 milligrams decayed 500 milligrams in 5 days. We're going to let m sub t be the mass of bismuth 210 in milligrams t days after the initial sample of 1,000 milligrams begins to decay. What it wants you to do is it wants you to set up and then solve an initial value problem for determining what m sub t is going to be. So really, we're just repeating what we did for part 1 of the previous problem, except now we have some different conditions to work with, right? And so again, the key point here is that bismuth 210 decays at a rate proportional to the amount present. So just like the previous example, because the rate of change is proportional to the amount present, we have that m prime of t is equal to k times m of t, where this function determines mass, and this is the rate of change of mass that's occurring. And so because we know that the derivative and the original function are related in this proportional way, this tells us that we know that the general solution is the following form. So we have m of t is going to be equal to d times e to the kt. So this is the general solution. And so just like the previous problem, we want to determine what d is equal to. We want to determine what k is equal to. We're told in the beginning that we had initially a mass of 1,000 milligrams. So we know that d is going to be equal to 1,000. But I guess I'll just write this out again. So just like the previous problem, we have 1,000 is equal to m evaluated at 0. So this is just equal to d times e to the k times 0. This is just equal to d. So again, we see that d is equal to 1,000. And so this is telling us that we have that m of t is equal to 1,000 times e to the kt. And then we're also told that, let's see, a sample of bismuth 210 initially had a mass of 1,000 and it decays 500 milligrams in 5 days. So like what this is really telling us is, well, we don't know what k is equal to, but like this is really saying like the half-life is 5 days, right? Like it decayed, it was started at 1,000 milligrams, went to 500 in 5 days. So we know that the half-life is going to be equal to 5. And so if you really wanted to, I'm not going to do it this way, but you can really say like 5 is equal to the natural log of 0.5 by k. And then you can just see that you're going to end up getting that k is equal to the natural log of 1/2 divided by 5 using this equation here. But I'm actually going to derive it. We'll just derive it normally. Right. So we have that after 5 days, we have the milligrams is equal to 500. So this is going to be equal to m evaluated at 5. We also know that this is going to be equal to 1,000 times e to the k times 5. And so now you just solve for k. Once you solve for k, we'll know what the particular solution is going to be. So you can divide both sides by 1,000. So you do 500 divided by 1,000. That's going to give you 1/2. This is going to be equal to e to the 5k. You take the natural log of both sides to get that natural log of 1/2 is equal to 5k. And then if you divide both sides by 5, you get the natural log of 1/2 over 5 is equal to k. So if you plug this into a calculator, right, this is just a number. And so the number ends up being minus 0.139. So we have k is equal to minus 0.139. And so in total, putting everything together, we have that the particular solution is m of t is equal to 1,000 times e to the minus 0.139 t. And then from there, if you need to determine like the mass at a certain time, you just plug in whatever the time is for t. And so what I was saying before, so like what we ultimately found was that k was equal to the natural log of 1/2 divided by 5. So we were able to derive it just by using algebra, but you can also just use the equation that I have written here, right? The example that we just saw, right? We saw that the half-life was equal to 5. So this is really saying we had 5 is equal to the natural log. I don't know why I wrote 10. This is a natural log of 1/2 over k. And so if you solve for k, this would just tell you that k is equal to the natural log of 1/2 over 5, which is exactly what we saw, right? So you can use it, you can like plug in like 500 is equal to m sub 5 and then solve for k, or you can just use the fact that we always have that the half-life is equal to the natural log of 1/2 over k and then solve for k. Okay, any questions about this example? Okay, yeah, so there'll definitely be a problem on the final for it to do something like this, where I give you like some function whose rate of change is proportional to the original function, and then you have to find what the particular solution ends up being. It's like guaranteed on the final that it will show up. So this is a good example to look through before the final, as is this one. And there'll be like practice problems that I give you as well. Okay, so I just want to go through a little bit of section 9.2. There's like, I think 2 or 3 problems on the homework next week that makes use of what we're doing here. And I guess really you don't need to, and you could solve this just by using the fact that we're looking at separable differential equations, but it'll be nicer to just have like an equation at hand that you can refer to. And so in this section, we're going to be looking at another class of separable differential equations that are just a little bit different from what we were looking at like 20 minutes ago. So we're going to be looking at differential equations of the form of dy dt is equal to k times y minus b, where we're assuming that both k and b are going to be constants. And so it's similar to what we were doing in that, like, we're looking at a rate of change that's proportional to something times y, or to something involving y, except now, like, we're looking at the rate of change that's proportional to the difference of y minus b, right? So it doesn't really add too much new stuff. It's just going to make it so the general solution is going to be added by some constant. But we're going to look at, like, we're looking at this in particular because this actually models some really important differential equations. Like, we'll be looking at like the heat equation later on or throughout most of this chapter, which is like a really important kind of differential equation in physics. And then it also models vertical motion involving like gravity and air resistance. Okay, and so this differential equation can be written in the following form. So if you multiplied everything out, you have like dy dt is equal to k times y plus some constant. The constant would be like minus b times k. For this reason, it's called a linear differential equation because the relationship between dy dt and y is linear. Let's see if there's anything else I want to say. Yeah, and so eventually we'll be looking at more general classes of linear differential equations, particularly in section 9.5, but we'll talk about that sometime next week, probably like Wednesday or Friday of next week. And so if we're given, again, like these differential equations, like the main thing we're interested in is like solving these differential equations. And so that's what it wants you to do for the next example. It wants you to find the general solution to the following differential equation. So we have dy dt is equal to k times y minus b. And so this really isn't that different from what we just did, right? So if you want to solve this differential equation, this is still just a separable differential equation in that we have a function with respect to y multiplied by some function with respect to x. The function with respect to x is just equal to k in this point at this for this problem. So we have, it's writing things out normally. It says dy dt is equal to k times y minus b. And so what we want to do, as we always do with separable differential equations, is we want to have everything with a y on one side of an equation and everything with a t on the other side. And so you divide everything by y minus b and multiply everything by dt to get that dy over y minus b is equal to k times dt. And then from here, you want to get rid of the dy and the dt, so you integrate both sides of the equation. And then after this, you want to solve for what y is going to be. So this is going to be equal to the integral of k times dt. And so the integral of y minus b with respect to y is just the natural log of y minus b. So we have the natural log of y minus b. This is going to be equal to k times t plus c, exactly like we had for the previous equation that we derived. And then from here, we want to solve for y. So you raise both sides, you exponentiate both sides with base e. So you have e to the natural log y minus b is equal to e to the kt plus c. Instead of writing e to the kt plus c, I'm just going to write it as this is equal to a times e to the kt. Using the exact same trick, right? You can separate this as a product of exponential functions. Then e to the c is just a constant, which we'll denote by a. And so this is really saying we have y minus b is equal to a times e to the kt. And then from there, you just add b to both sides, right? So you have y is equal to a times e to the kt plus b. And so this is the solution that we find. So it's exactly the same as what we just did, right? Like before we were just looking at k times y, and this is what we found for the general solution. And now with having like this minus b show up, you just add b, right? That's all that's going on now. It's the only change. Any questions about how I derived this general solution to this equation? Okay, and so now that we know what the solution or general solution is, like you don't really have to derive this again. I mean, on the exam, I could ask you to derive this equation. I feel like that would be pretty fair game. But like, if you have an equation of the following form, you just have to use this equation now and fill in, right? So what we just showed is that the general solution of dy dt is equal to k times y minus b. It's given by y sub t is equal to b plus c times e to the kt. I guess I wrote the constant as a. They write it as c. So it's the same thing. You're multiplying by some constant, right? And so now if we want to find the general solution, so we have the following differential equation. So after I'm done with this example, I'll pass out the exams and we'll talk through it. And then on Monday of next week, we'll talk about this cooling equation. So this is actually the first differential equation that we looked at on Monday. I think it's like the first example. Or yeah, it was like this example right here, right? Oh, I guess it's a little bit different. Wait. Oh, I guess I'm just misremembering. I guess I shouldn't have said that. Never mind. Forget what I said. It's similar to the first one that we did. I guess it's a little bit different. Okay, so we have something of the form of like y prime plus 7y is equal to 21. And we want to find the general solution of this thing. It doesn't look like it's of this form, but the trick is like if you just, subtract everything by 7y and you factor by 7, you end up getting something of this form right here, right? So what we're saying is we have dy dt plus 7y is equal to 21. And so what you can do is you can subtract both sides by 7y. See, like the difficulty would be like if you multiplied everything through by dt in the beginning, you have like 7y dt, which is going to mess things up. So you can't like integrate right away, even though we have like a dy and a y on the same side of the equation. So what we're going to do is we'll subtract both sides by 7y. So we have dy dt is equal to minus 7y plus 21. And so what we can do here is we can factor out a 7 from this equation. So this is the same thing as having a 7 times minus y plus 3. And then you can rewrite this. Like it's a little bit wonky in that we should have like y not being multiplied by minus 1, and we have like a minus 1 here. So you can really rewrite this as being equal to minus 7 times y minus 3. So condensing this chain of equality that we have, we found that dy dt is really equal to minus 7 times y minus 3. Right, and now we have it exactly where we want it, so to speak, right? Like we have something of the form of like k is equal to minus 7, and then we have that our b is equal to 3, right? So like this is really saying that we have k is equal to minus 7, referring to this equation that we have here. And then we have that b is equal to 3. And so now it's just a matter of plugging terms in. So if we have a differential equation of this form, we know that the solution is just going to be b plus c times e to the kt. And so we won't solve what c is, like we don't have enough information to determine what c is, but we're going to be, like this tells us that we have that y sub t, like the general solution is going to be 3 plus c times e to the minus 7 times t. Right, so again, I'm just using this formula here. If you have a differential equation of this form, we know the general solution is of this following equation. And we know what b is equal to, and we know what k is equal to. So you don't have to go through with like integration, right? Like you don't have to go through integration and solve for y. Instead, you can just plug into this equation. Okay, any questions about this example? Yeah.
You can also get that going through integration, right?
Yeah, you can just use the same techniques we've already done. like from here, you can divide both sides by y minus 3. You would integrate both sides, like natural log of y minus 3. And then you would have to solve. It's like more work, but yeah, if you don't want to, like, technically you don't have to memorize anything, or you don't have to put this on your note card, but it's easier. It's like you can skip a lot of steps. Okay, any other questions? Okay, so this is where we'll stop. We'll pick up on like Newton's law of cooling tomorrow, or on class on Monday, so we don't have class on Friday. So I'm going to segue to talking about the second midterm. So I posted the solutions online. You should have gotten an email about that. So I'm going to pass these back. Oh, I was like, Jack. Anna, Daniel, Serena. Okay. Owen. John, Arnie. Anna. Ryan. Warren. David. Thomas. Ben. Nathan. Okay. Did everyone get their exam done? Okay. Yeah. So this one was kind of it was kind of like it was like mixed. It was like either you got it or you didn't for the most part. So this is like the distribution of scores. It's like the most common grade ended up being like an A minus. So like from the 45 to 50. So for a lot of people, the exam went well. But there's also like around like half the class that got below like a 40 or so. And so I think like the main thing is I think like it's like halfway through the semester, so like everyone's tired, and like a lot of you have like math isn't your highest priority. I understand that, but it's important to like go through the exam review. There's like 3 problems that I put on the exam. That was from like one of the reviews. So just like talking through a few of the problems, like it's important to know. Like I think problem 2 gave people a lot of difficulty. because I think they were trying to do integration by parts, which is a valid way of doing things. And some people were able to go through it correctly. But like the main trick is you can rewrite hyperbolic sine in the following way, just using the definition of hyperbolic sine. If you do this, you end up getting something that's a lot easier to compute. This was a problem that was on it was like on the practice exam on Tuesday of last week. It wasn't exactly the same, but it was like the same idea. This is like from the group work from last Tuesday, like the exam 2 review group work. So there's like a similar problem last week on Tuesday. Problem 3 was also one that people had difficulty with, but this is also a problem that just came directly from the exam review. So this was like problem 10A right here. So it's like kind of the expectation for like the exam review problems is like, I feel like if it's on the exam, like I kind of view them as being like 3 points. Like they are, like I'm not saying this is like an easy problem, but like you need to make sure you go through the exam review. So for this one, if you want to find the arc length, like you just take the derivative of y, and then you do like the equation, and you simplify a little bit, get like the following equation. Yeah, so this one, I mean, it went well for the most part, but for some, like even doing like the derivative gave difficulty. I think problem 4 was probably the hardest problem on the exam, just because it's like a partial fraction problem. Like it requires the most amount of writing. Like I think all the other problems you can do within like a couple of equalities or a couple of steps, but this one, like it requires a lot of work. This one actually went pretty well for the most part, aside from maybe like a miscalculation here or there. But I tried to be like somewhat generous and not take off too many points. If you showed like kind of knew what was going on and just made like a slight mistake somewhere. Problem 5, I kind of like underestimated the difficulty of this problem. So for problem 5, this turned out to be like a difficult problem for a lot of people. And I think it's because it's like less computational and more conceptual. So for problem 5, it wants you to find the volume of A, or the values of A, to make it so this integral converges. And so you need to find a value of A that makes it so like this will end up giving you a finite number. And so what you do is you just integrate this equation and you get 1 over A times e to the ax. This is like one of the fundamental integrals. Like it's one of the first ones you learn in Calc 1. And then from there, you have to determine like the limit of this as x goes to infinity, essentially. So you end up getting the following equation. And so if you plug in x is equal to r and you let r go to infinity, you end up like the only thing that involves r is this exponential function here. And so you just need to think like, how can I make this end up being a finite number? So if this like exponent is positive, then this means this whole thing is going, well, it means you're going to infinity, and e to the infinity just goes to infinity. But if you have like a negative exponent, like say you have like e to the minus r or something, like this is just equal to 1 over e to the r. And so if r goes to infinity, like this just goes to 0, right? So this goes to 0 as r goes to infinity. So that's like the main point. Like as long as this exponent is negative, like you end up just going to a finite number. So you just have to have that a is less than 0. Otherwise, like this is just going to go to infinity. So it's like more conceptual than anything.
Why can't it be 0?
Oh, I mean, it could be 0 if you didn't have 1 over a. Like if you plug in a is equal to 0, then like this will give you some problems. Okay, and then problem 6. This one just came from the group work review as well. So like this problem was just like this one with the same numbers. And then problem 7, what you have to do for problem 7 is you just have to show that this, if you integrate this function, x times e to the minus x from 0 to infinity, you just have to show that this ends up being equal to 1. So this is really just like an integration by parts problem. We have to do a limit at the end. So if you take this integral, you end up getting the following function. You evaluate from 0 to infinity, you end up getting the following limit. And then everything kind of just turns to 0 except for like this 1 at the end. So you end up just getting a 1. So you show that this integral ends up being equal to 1. So it's a probability density function. Yeah, so for the most part, the exam went well. I think like the one thing I want to like really hammer home for like the final is like make sure you do like the exam review. Like it's important that you understand what's going on. And usually I put in like 2 or 3 problems from the exam reviews onto the exams, and it'll hold true for the final as well. So if you have any questions about the exam, you can ask me. And I also put the solutions online. You should have gotten an email about it yesterday. Yeah, so we'll continue differential equations. This is the last midterm, so all that's left is the final at this point. And the final will be cumulative, so there might be like a repeat problem from exam 2 on the final.
For the final,
What's that?
do you review like the two exam or for the final or the notes? Like the exam?
Oh, I'm not understanding the question. Are you saying?
For the final exam, do we, like review the old exams?
Oh
or
yeah, I mean it'll
just
be
notes?
half and half. So it'll be well, I mean, like whatever you have at your disposal, right?
Okay.
I mean, it'll be like half and half in that, like it's 100 points, so 50 will be on old material, and then 50 will be on like the differential equations.
Okay.
And I mean, it'll be good to like if you work through the exams. I mean, those are problems I used in the past, so it
Okay.
might show up again. Yeah, so anything? Yep. Yeah. Question.
Quick question.
Mhm.
This question on the exam I had a brain fart, but